Okay, welcome back. This is a video for particularly the specialist methods students on compound and double angle formulas and just how to apply them in some different situations, similar to the ones that we did in class, but just a tad different, okay? As always, feel free to pause before I do each example to give it a go yourself and check my solution, or just keep going if you want to see how it's done. All right, let's do example 1. Find the exact value of tan of 5 pi on 12. Okay, so the first thing that we should notice is we notice that 5 pi on 12 is not an exact value angle from our triangles. Okay, which means immediately our mind should go, okay, I either need to be using double angle or compound angle. Now, double angle is probably not going to be very helpful here because if I double it, I just get 10 pi on 12, right? But actually, that could be kind of helpful. I guess you get 5 pi on 6 and you can do some stuff with that. Maybe if you want to as an application, you could try doing that yourself. Yeah, so maybe I'll just even write this as an extension. I'll write it in the bottom so that way you can see it afterwards. As an extension, try using actually, no, I don't think that's going to work. You're going to end up with not enough information. Okay, ignore everything I just said in the last 2 minutes. I can't be bothered to re-record this. Okay, not an exact value angle from our triangles, which means we have to use our compound angle formula. We have to find a way of rewriting. So can we write this as a compound angle? And most of the time, because we're playing the game on easy mode, the answer will be yes, right? So we can say, let's do it in blue, 5 pi on 12 is equal to, and now we're just going to look for ways that we can split up this 5 pi on 12 to simplify our fraction nicely. So there's really only a couple of options, which is nice, and it's going to be this. Okay, which simplifies to pi on 4 plus pi on 6. Very nice, right? And those are exact values. Yay. Or exact value angles. Smiley face. Okay, so now we're good to go. Now we can just apply the tan compound angle formula and we can work from there. So our tan compound angle formula says tan of pi on 4 plus pi on 6 is equal to tan of pi on 4 plus tan of pi on 6 divided by 1 minus those two things getting multiplied together. Okay? All right. Now we can apply some exact values. Again, because you have the ability to pause, I'm not going to explain how I'm getting these. I'm just going to draw the triangles and you can pause as you need to, okay? This is literally just for my reference. Root 3, 1, 2, pi on 6, pi on 3. Okay, so equals 1 over root 2. No. Lol. Getting it wrong straight away. 1 plus tan of pi on 6 plus a half. Okay, plus a half. No, what am I? Oh my goodness. I'm not going to tell you exactly what time I'm recording this at, but judging from the amount of mistakes that I'm making, I'm sure you can figure it out. Divided by 1 minus, well, the tan of pi on 4 is 1 times 1 on root 3. Okay, which is equal to, all right, so now we just have to do a bit of fraction simplification. It's going to be root 3 plus 1 over root 3 divided by, just going to write it as a division now because it's easier with the fractions, divided by 1 minus 1 over root 3, okay, which is equal to root 3 plus 1 over root 3 divided by root 3 minus 1 over root 3. So then we can just KFC it, flip. So flip, change this to a times. So it becomes, well, actually that'll be nice because now these root 3's will cancel out. So we get root 3 plus 1 over root 3 minus 1. Okay, now there actually is a further step here. We haven't talked much about rationalizing the denominator because, you know, it's just an algebraic thing. It doesn't change the exact value of your answer. So unless I tell you to do it, you don't have to do it. But we're going to do it this time. We're going to times by root 3 plus 1 to apply a difference of perfect squares to the bottom. Okay. Because if we times by itself, we would get some cross terms like the 2ab in our quadratic expansion or our binomial expansion. So we don't want to do that. We want to do a difference of perfect squares, which gets us root 3 plus 1 squared over 3 minus 1. Which is quite nice. Which equals, keep giving ourselves more space, equals root 3 plus 1 squared over 2. Okay, which is kind of nice. And then obviously you could keep going, but we're not going to. This is perfectly sufficient as an answer. Cool, all right. So that's an example of how to use the compound angle. Usually just involves splitting up the fraction and working from your exact values. Example 2, find the exact value of whatever this thing is. Now, this is a case of where you could try to brute force it. You could apply a lot of double angles and then sub them all in, and you should get the same answer. It would just be horrific. So here we recognize this is an expansion of the compound angle. Of, not the, let's say, oh no, we can say the compound angle formula for, and then you can just check your formula sheet, sine of a plus b. Cool. Which is good, because then it means that we can actually just replace all of this with a nice angle expansion. So we can say this whole thing is equal to, well, this is A, and this is B. A, B. Actually, let's do it in a different color. Boom, boom, boom. A, B, A, B. So we could say the whole thing then is equal to the sine of pi on 12 plus 7 pi on 12, which is equal to the sine of 8 pi on 12, which is equal to the sine of divide by 4, 2 pi on 3. Okay, and then we just go work out what the sine of 2 pi on 3 is. I'll do it fast, but if you want to take a second, you can do it. I know that my exact value triangle tells me this is pi on 3, this is pi on 6, this is root 3, this is 2, this is 1. So the sine is going to be sine of pi on 3 equals root 3 on 2. But I know this is 2 pi on 3, but this is in the second quadrant. So sine is positive. Okay. So I can just keep it as it is. I can say, so, which is equal to root 3 on 2. Cool. Which is nice. Good to go. Which I can guarantee you would have gotten if you did all of this with some yucky double angles, but why bother? Just add them together. All right, this should be example 3, sorry. Gave you an extra one. The last one. If cos of theta equals 3 over 5, where theta is in between 0 and pi on 2. Find the exact value of sine of 2 theta. Okay, so this immediately tells us we're going to use double angle for sine 2 theta. Okay, so maybe let's just write that out to begin with, and then we'll see what we need. Sine of 2 theta is equal to 2 sine theta cos theta. Now we have cos theta. It's here. But we don't have sine theta. So we need this. So we ask ourselves the question, so where do we get sine theta? And the answer is not divide by 2, right? The answer is, well, what identity relates sine and cosine together? So when I have one of them, I can find the other one. Use the Pythagorean identity. The Pythagorean identity. So this tells us that sine squared theta plus cos squared theta is equal to 1. The Pythagorean identity is so cool. It comes up everywhere. You can apply it whenever you want. You just might not need what you get, right? But in this case, we need sine theta. So we're going to go get it. We know what cos theta is. It's 3 over 5. So sine squared theta plus 3 over 5 squared is equal to 1. Therefore, sine squared theta is equal to 1 minus 9 over 25. So sine squared theta is equal to, I think it's going to be 16 over 25. Whoa, that's cool. So we go back up here and we say, so sine theta is equal to the square root of 16 over 25, which is equal to the square root of the top and the bottom, so 4 over 5. Now, there's one thing that we have to check. Do we put a minus on this? Negative? No, because of this. This told us that theta was in between these two things. Sine is positive here. Okay? If you had to write that on a test, that would be sufficient. You can just draw an arrow point and say, no, it's positive here. Okay? All right, so now we have it. We have sine theta equals 4 over 5. So now we can apply our double angle formula. Sine of 2 theta is equal to 2 times, well, the sine of theta is 4 over 5. The cos of theta was 3 over 5 from up here. So the sine of 2 theta must therefore be equal to, well, we just multiply these things together. So I think we get 2 times 4 times 3 is 24 over 25, which you'll note is not, it's written in red because it's important, note, this is not 2 times sine theta. Okay? Great. All right, so there's your 3 examples of how to use the compound and double angle formulas. Again, go back and watch it if you need to. Take a pause to figure out any algebra. Hope that's helpful. Happy practicing.